Okay, hello, welcome back. In the previous video, we started analyzing the motion of a point on a rotating body or a general planar motion, motion of a point on a body that undergoes general planar motion using rotating frames. Position was easy. Now next step is velocity. And to analyze velocity, let's start with position. So I had, oops, why is it green? R of B is R of A plus R of B relative to A. All good. So let me quickly remind what the setting is. We have the little frame XY that is fixed to the body and rotates and moves with the body with angular velocity omega, big omega. And point B is a point on the body, but it can move around on the body. So it's not a fixed point. So that is the setup. The position, if we know relative position of B as observed by observer A, we can use this vector equation to solve for position. If that is the position of B, I can take derivative of it. D over dt of R of B is d over dt of R of A. These are the absolute position vectors plus d over dt of R of B relative to A. Okay, this is what we expect. This one is what we are trying to find. This is velocity of B in the base frame equals, this is velocity of A in the base frame plus something. This something is actually quite something. I'm not going to derive it, but note that if point B is somehow fixed, a fixed point on a space, as the observer A moves around and turn and rotates, we are going to see some velocity, and that must be compensated by this last term. The derivation is in the textbook, but as it turns out, it is going to be V of A. All of this is going to be V of B relative to A as observed in the XYZ frame plus this omega cross R of B relative to A. All of it is the last term, and this is vector, that is vector. So derivation is in the textbook. Let me clean up here. But let me unpack what this means. So V of B equals V of A plus whatever relative velocity exists, but what that relative velocity is. The first term, this one, the first in the relative velocity context, is the actual, it's missing something, actual relative velocity observed or measured by A, and the second term, this one is somehow the rotational effect. Well, no, let me do this. Let's do this. Velocity induced by rotation of observer. Let me try to relate this to a very familiar case that we already know. I'm trying to redraw everything. This is the body, this is A. Let's, for simplicity, assume point B only goes back and forth along a straight line. So what we could do in the past, and we have studied this in the past, I made a coordinate frame like this. This was some angle theta from a fixed horizon, for instance. This is smaller than I like. Make this bigger. And I don't need this. We used to call this UR, and we used to call this U theta. Now, if point B moves back and forth, what you end up with is, let's write it as V of B is V of A plus this relative motion. But relative motion, we can describe it in the polar frame. It is some R dot of B relative to A, however much the distance is changing in the UR direction, plus some R of B relative to A, that distance, times angular velocity, theta dot, in the theta direction. We had these. And this is exactly what we have here. We have the first term, we called it V, in this new formulation, it's V of B relative to A as observed by this frame XYZ. And this second term is our omega cross R of B relative to A. So these are the same formulation that we always had. But what we have now in this vector equation is more general. Point B doesn't need to move just along a straight line as we considered in this dummy example. B can go anywhere, and if that happens, what you observed as relative velocity of B relative to A, in that case, some of it would essentially trickle down into the other term, and what you end up with is the correct velocity of B in the reference or base frame. So that is velocity. In essence, it is really nothing more than a relative motion analysis using the polar frame. It is written in a slightly fancier and more general purpose language. That's all. Actually, now that we are here, let me make one last connection. And that is what happens when omega is 0. When omega is 0, essentially your frame doesn't rotate anymore. So you have translational frame. And you would expect to recover the same equation we had before. So let me write that down. V of B is V of A plus V of B relative to A as observed by XYZ frame plus this omega times r of b relative to a, which is 0. And this is what we had. Wait a second. What did I want to say? Is this what I wanted to say? No, I don't know what I wanted to say. Yeah, I don't know. My example wasn't the best. So for now, skip this. I'll think about what I wanted to say more. I don't remember exactly. I didn't write proper note. But I'll talk about this in class. So I think that is what I wanted to say. So let's keep it as this. So we have the velocity. Let's do acceleration and we wrap this section up. So I'll see you there.